In our previous videos, we covered about binary tree and binary search tree. We understood how binary search tree work. Basically, for each node, the smaller values are added to the left side of that node and greater values are added to the right side of that node. But there is a problem with the binary search tree. Binary search tree can become unbalanced after multiple insert or delete operations. So based on the insertion and deletion order, the binary search tree can become unbalanced. Let's understand how. So let's say we are inserting this value in this order to binary search tree. So the binary search tree will look like this. First, it will add 60. Then it will add 50 as the left child of 60 because 50 is less than 60. So it will go on to the left side. Then 40 will get added as a left child of 50. And similarly, 30 and 20 will get added. Now you can see our binary search tree will look like this if we insert these numbers in this order. Now, the same numbers, if we insert in this order, like 50, 30, 60, 40, and 20, then our binary search tree will look like this. Now you can see we inserted the same numbers, only the order of insertion is changed. So you can see how the structure of tree is different in both the cases. Now, in a first tree, the height of the tree is 5. And in a second tree, the height of the tree is 3. Now, if you want to search 20 in a first tree, we'll have to go till end of the tree and then only we'll find the 20. So in a worst case, the time complexity in such cases where the tree structure is like this is O of n. N is the number of nodes in a tree. But for this tree, when we want to search 20, you will start from 50 and you will ignore the right part because you will go on to the left side. 20 is less than 50, so you will go on to the left side. And you will come to 30, then you will again go on to the left side because 20 is less than 30. So every time we are removing the half part from the search space. So that's why the time complexity is O of log n. So you can see, depending on to the height of the tree, our time complexity changes for our search operation and similarly for our insert and delete operation as well. So we need to basically we need to find out the way to self-balance this tree to achieve the minimal height like this. Because if you see the numbers are same, but the way they are represented is different and it impacts the height of the tree, which eventually impacts our tree operations. So we need a way to self-balance the unbalanced tree to achieve the minimal height. And that's why the balanced tree comes into the picture. And there are different balanced trees, and AVL tree is one of the balanced tree. The AVL tree is a type of binary search tree that rebalances itself or basically does the self-balancing whenever it becomes unbalanced due to insertions or deletions. Now, each type of balanced tree have its own way to rebalance itself, or each type of balanced tree have a way to define whether it became unbalanced. So when does AVL tree consider itself unbalanced? Now, each node in AVL tree has a balance factor. What is that balance factor? The balance factor is balance is equal to height of the left subtree for that node minus height of the right subtree. For example, let's say this is our binary search tree. For node 50, the balance factor is height of the left subtree, which is 1, 2, minus height of the right subtree, which is 1. So 2 minus 1, it is 1. Similarly, for node 30, the balance factor is height of the left subtree and height of minus height of the right subtree, which is 1 minus 1, 0. And for a leaf nodes, the balance factor is 0 only because for leaf nodes, there are no left and right chain. So AVL tree allowed balance factor is minus 1, 0, and 1 only. If the balance factor is not one of this value, then AVL tree considers itself unbalanced. So after insertion or deletion, if any node's balance factor is not minus 1, 0, or 1, Then the tree becomes unbalanced and AVL tree will perform the rotations to fix it. Basically, rotations is a process to make the tree again balanced. Let's understand the idea behind self-balancing technique in a AVL trees. We understood when does AVL tree consider itself unbalanced. Now let's understand what is the idea behind making that tree balanced again. So let's take this example. So this is our binary search tree. And let's, for each node, you can see the balance factor is like this. For 30, the height of the left subtree is 1 and height of the right subtree is 2. So 1 minus 2 is minus 1. And similarly, we calculated the balance factor for each node in this binary search tree. So far, for every node, the balance factor is either 0 or minus 1. So it is fine. But now, when we want to insert 32, now, according to the binary search tree property, 32 is greater than 30, so it will come to the right side. 32 is less than 35, so it will come to the left side. And 32 is less than 33, so that's why 32 will get added here. Now, when we insert 32, what will happen? Let's see. The balance factor for 32, which is a leaf node, it will be 0. Now, from the new inserted node, if we go up, we need to see the balance factor. Now the balance factor for 33 changed to 1 because it is 1 minus 0, which is 1. The balance factor for 35 is 2 minus 1, which is 1. Now the balance factor for 30 is the height of the left subtree is 1. The height of the right subtree is 3. So 1 minus 3, it is minus 2. It means that our binary search tree became unbalanced according to the rules of AVL trees. Now, if we see, this 30 is the root of the unbalanced subtree. So this is the unbalanced tree and 30 is the root of it. And the right child of that root, which is 35, is the subtree which is making this whole tree as unbalanced. How? If you see, previously the height of the left subtree was 1 and height of the right subtree was just 2. But now when we add a new node, the height of the right subtree changed to 3. So the right subtree is making this whole tree unbalanced, where 30 is the root. That's why we say one node is basically the right side of the 30 is making it unbalanced. And where we added the new node, basically we added to the new node 32 is added to the left child of the 33. So just keep in mind these 3 nodes. We'll come back why we selected these 3 nodes. So let's understand from the another example. Let's say this is our tree, binary search tree, where for leaf node, the balance factor is 0. And the balance factor for internal nodes is like this, calculated from height of the left subtree minus height of the right subtree. Now you can see for every node, the balance factor is either 1, 0 or minus 1, which is allowed for AVL tree. So it is a balanced binary search tree. Now let's say we want to insert 52 in it. Now what will happen? The balance factor for 52 is 0, right? Because it does not have any left or right chain. Now balance factor for 55 is 1 because the height of the left subtree is now 1. So 1 minus 0 is 1. The balance factor for 60 is 2. Now, the balance factor for node 60 is 2, so it means it is unbalanced. So, this is the smallest impacted area of whole tree. So, we need to only focus on smallest impacted area, like similar to here. So, if you see here, what is the smallest impacted area? Basically, when which is this early node which became unbalanced, starting from newly inserted. This is the node. So this is the root of the smallest tree which became unbalanced, 60. And because of which subtree it became unbalanced? It became unbalanced because of the left subtree. What is the root of that left subtree? It is 55. And for this 55, where did we add in that new node? We added onto the left side. That's why this is the third. So basically the idea of AVL tree is instead of thinking about whole tree, we need to check for the least impacted or smallest impacted area, which we can easily get from this three nodes, right? So AVL uses this idea of three nodes to find the smallest impacted area and then work on balancing on that smallest impacting area only so that whole tree becomes balanced automatically. What are these three nodes? First node is the root of the smallest unbalanced subtree. The second node is the taller child of Z, because of which this subtree became unbalanced. And X is the child of this Y along the path to newly inserted node. Basically, it is the node which is either the newly added node or the new node is added as a child of that node. Right? So that's why, because the AVL tree works only with these three nodes and only with this smallest impacted area, that's why the rotation of the AVL tree is fast or O((1) only. Now we understood the idea behind the self-balancing technique in AVL tree. We need to find the three nodes, which are basically representing the smallest impacted area or smallest unbalanced subtree. And once we rotate that impacted area properly, then we can get the balanced subtree like this. Okay. But now the question comes, how can we identify this smallest impacted area? Basically, each impacted area, because of the three node structure, right? The three node structure can be of different type, right? Like AVL tree finds three nodes, Z, X, Y, and work on rotating them to self-balance. What is Z? Z is the root of the smallest unbalanced subtree, which is basically smallest impacted area. Y is the taller child of Z, because of which the smallest subtree where Z is root became unbalanced. And X is the child of Y, which is basically along the path where we inserted the new node. Right? It could be new node or it could be the parent of new node. Now these are three nodes. So because the three nodes, how they can be represented? Let's say Z is the root of the smallest unbalanced subtree. Now Y is the taller child of Z. Now Y can be left child of Z or Y can be right child of Z. Right? Now X is a child of Y. Right? So X can be either left child of Y or X can be either right child of Y. So we can see that the three nodes which we will find for the smallest unbalanced subtree, they can be in any one of this structure. So these four possible structure are there. And for each structure, the rotation or the self-balancing logic is different. That's why we have four rotations, right? So what is this each structure represents? The first structure is left imbalance. Basically, what does that mean? That the subtree, the smallest unbalanced subtree where Z is root, it became unbalanced because of the new node added on to the left side. And node added to the left of it, basically as a X, which is the parent of the new child, or as a new node itself, right? So it is called as a left situation, right? The second situation is left imbalance. It means that Z became unbalanced because of the heavy left side only, but new node is added as a right child of the left subtree, right? Or added on to the right side. That's why the situation is left right. Similarly, the situation here is right imbalance. The Z became unbalanced because the right subtree became because of the right subtree, right? And but the new node is added as a left side of the right subtree. That's why it is right left. And the last is right right. Z became unbalanced because of the right subtree, and the new node is added onto the right side of that right subtree. That's why it is right right. So these four situations we need to handle. And for these four situations to get handled, we need to handle it using 4 different type of rotation logic. So let's say this first situation, which is left, right? Z became unbalanced because of left subtree, and new node is added as a left child of this left subtree. So it is left. So for this, to solve this situation, the rotation which is used as the right rotation. We'll understand why. A right rotation is used when node is too heavy on a left side. Now Z is heavy on a left side, meaning it is left imbalanced, right? So it rotates the tree to the right side to fix the imbalance, because now we are actually imbalanced onto the left side. How we can solve this imbalance? By rotating it to the right side, right? So we rotate the tree to right side, fix the imbalance, and make the tree more balanced again. Let's understand how. So to understand how the tree structure changes, we also represented here T1, T2, T3, T4, which are basically child of Z, Y, X, right? So when the rotation happens, how it will impact to this childs or subtrees of the X, Y, Z, it will be easy to understand. Now the steps. What are the steps for right rotation? Now tell me one thing. When we rotate this tree onto the right side, right? It means that we need to bring Y here, right? So the first step is the left child of Z, which is Y, becomes the new root. Okay. And Z becomes the right child of Y. Why? Because, see, if Y becomes root, then where will Z go? Z is greater than Y, right? Because that's why Y is on the left side of the Z. So that's why when we make Y as the root of the tree, then Z will become the right child of Y according to the binary search tree property, right? The greater values will be on the right side. Okay. Now, and then if any previous right subtree of Y, which is, let's say, T3, right? It becomes left subtree of Z. We'll understand why. Let's say we are performing this first two step. The left child of Z, which is Y, it became the new root. Good. And Z became the right child of Y. Right. So you can see X and Z structure is unchanged. Right. Now Y became the root. Z became the right child of Y according to the binary search tree properties. Now one thing you might have observed that the T3, which was previously the right child of Y, is now unlinked because right child of Y is now Z. So where this T3 will go? So if you see here, T3 was right child of Y. It means T3 was greater than Y, right? So it will be on the right side of the Y. Correct. But T3 was on the left side of Z. So T3 is definitely smaller than Z. So if T3 goes onto the right side of the Y, it will become the left side of the Z because T3 is less than Z. Right? So that's why if there is any right subtree of the Y, it becomes the left subtree of the Z so that it can still satisfy the binary search tree properties. The T3 is greater than Y, that's why it is on the right side of the Y, but T3 was smaller than Z, that's why it was on the left side. So it will remain onto the left side of the Z, right? So this is the right rotation logic. Let's understand with the example, right? So these are the steps we know. So this is the example. So this tree is, let's say we add 10 here. So the balance of the tree becomes 2, which is unbalanced, right? And because we need to find ZX and ZY and X. So what is the ZY and X here? So ZY and X is this. Why this? Because the smallest subtree which is impacted is this one, right? Because for 50, the balance factor is 2. For 30, the balance factor is still 2 minus 1, 1, right? So it is not unbalanced. So 50 became unbalanced. So this is the smallest subtree which became unbalanced when we added node 10. So that's why it is a Z, which is the root of the smallest unbalanced tree. And Y is 30 because 50 became unbalanced because of the left side. So that's why Y is the root of the left subtree, and 20 is x because the 10 was added as a child of 20. Now we got the z by x. How the right rotation will work here? It is left-left situation, right? So how it will work? How did we find it is a left-left situation? We find it basically if the balance of the tree is greater than 1, it means if it is a positive, and if the new node is added as a left child of y or as a left child of y's left child, right? That's how we find the left-left situation. So, sorry, I will rephrase and correct it. We find left-left situation by checking if the balance is greater than 1 and if the new node is added as a direct left child of y or if the new node is added as a child of left child of y. Either the direct child of y or added as a child of left child of y. T4 is basically, these are the T4, T3, T1, these are the subtrees, or we can say child of the ZYX, so that we will understand how the tree structure changes. Now step 1 and 2, left child of Z, which is Y, becomes the new root, and Z becomes the right child of Z. Z becomes the right child of Y. So you can see here, right? Now the T3 is now removed, right? Because Y is right child is now Z, right? So that link is removed. So where we will add? So as according to the rule 3, the previous right subtree of Y, which is 40, which is T3, becomes the left subtree of Z, because see, 40 is greater than 30, so that's why it will be on the right side of the Y. But 40 is less than 50, that's why any right child of the Y will become the left child of the Z during right rotation. So we'll perform the step 3 and we'll get the tree like this, right? So we can see the balance here now. The balance of the tree is now 2 minus 2, 0. So our tree became balanced, right? So we use the right rotation for left-left situation. Now let's understand the rotation logic for the next situation, which is right-right. So for this, we use the left rotation. Why? Because Z became unbalanced because of the right side of it, right? So we'll basically left rotate so that the tree will become balanced. The left rotation is used to fix the right-right imbalance in an AVL tree when node's right subtree is too tall. It rotates tree to the left to fix that imbalance and make the tree more. Now, what are the steps when we do the left rotation at Z? The Y becomes the new root of subtree, similar to right rotation. But now Z becomes the left child of Y in a right. But now it is left child of Y because see, Y is greater here, right? If you move Y here, then where the Z will go? Z should go onto the left side because Z is less than Y, right? That's why Z becomes left child of Y. Now to represent the tree structure or rotation properly, these are the subtree or the childs of ZYX, T1, T2, T3, T4. Now if Y had any left child, which is let's say T2, it becomes the right child of Z. Why? Because if Y becomes the root, then this link will go away. Now T2 is less than Y, so it will not be on the right side, it will go on to the left side. But where it will go, right? It will become the right child of Z because T2 is less than Y, but T2 is greater than Z. That's why it was on the right side of the Z, right? So the first two steps we did, Y became new root of the subtree, Z became left child of Y, and if Y had any left child, which is T2, then it becomes the right child of Z, so that the property of the BST will still be there. Let's understand with the example. So if you see here, this tree If you want to add, let's say 80 here, this tree becomes unbalanced. The balance factor at 50 becomes -2. So this is the smallest subtree which is impacted. Now we know how to find the z, y, x. Z is basically the root of the smallest unbalanced tree. And while insertion only we come to know that. Right? So if you go and check the AVL tree insertion logic, you will get to know how we come to know that whether that node became unbalanced or not. In next video, I will cover the implementation also. In this video, we'll cover the concept. So now the 50 became unbalanced because 1 minus 3 is -2. So it is the right subtree of the 50 is heavier. Now we'll do left rotation in this case. Because right. How did we come to know it is right? If suppose the balance of the node is less than -1, and if the new node is added as a right child of y or added as a right child of y, basically either as a direct right child of y or as a right child of y, then we come to know that it is a right situation and we need to do left rotation. Sorry, I will rephrase and correct it. We find right situation if the balance is less than -1 and if the new node is added as a direct right child of y or added as a right child of y. It means either the direct right child of y or it is the child of right child of y. So to better understand T1, T2, basically this represents the subtree which are connected to our Z, Y, X. Now if we do step 1 and 2, what will happen? Y becomes the root of the subtree. Z becomes the left child of the Y. Now 55 is basically the link between the Y and its left child is now removed because Z became the left child of Y. So we know that we have this step 3. If y had any left child, which is 55, add it as a right child of z. Okay. Now, from this example, you might have understood why we add a left child of y as a right child of z. Because 55, initially 55 was on the right side of z. Right? Now, when this link removes, like when this 55 does not remain the left child of y, where should we keep it? It should be on the left side of y only. Now y is the root, so it should be on this side only. But where? Now 50 is less than 55. That's why it will be as a right child of z. It will become as a right child of z. Because y was a right child of z, right? So now y is removed as a right child of z. So there is nothing on the right child of the z. So there is an empty position here. So that's why we add a T2 as a right child of z. Now next situation. We'll understand the rotation logic for this situation. What is this situation? So this situation is basically it is a left unbalanced. So Z became unbalanced because of the left heavy subtree. But on the left heavy subtree, the new node is added on to the right side, either as a right child of Y or either as a basically either as a left or right child for the right child of y. Right? So this is the left and right situation, zigzag. So that's why in this case we need to use the left-right rotation. So the left-right rotation is used when AVL tree is a left heavy, but unbalance is caused by the right child of the left subtree. It performs left rotation at y and the right rotation at z. So it performs a double rotation or 2 times rotation. We will understand why 2 times rotation. So to understand more better, we are representing this T1, T2, T3 as a child or subtrees of the z, y, x. So now why 2 rotations? So first thought comes that z became unbalanced because of the left side, right? Left subtree. Then why can't we just do the right rotation? Okay, let's do it. So if you do the right rotation, what will happen? In the right rotation, y will become the new root. Good. and Z will become the right child of Y. Good. And if Y had any right child, then it becomes the left child of Z. Okay, we did the right rotation. We thought that heavy left side. So why can't we just do the right rotation? We did the single rotation. Fine. But the tree is still unbalanced. Right? Previously it was unbalanced at Z, like 3 minus 1, 2. Now it is unbalanced at Y. So we did not solve the unbalance problem. The tree became unbalanced again. Previously it was at node Z. Now it is at node Y. Right? 1 minus 3 minus 2. So it is still unbalanced. That's why the single rotation doesn't work here. Now, if you see, this is a zigzag pattern. If you want to use a single rotation, like left rotation or right rotation, we need to have Z, Y, X either in one direction. It should be either as a Z, Y, X or Z, X, Y. Can we convert it into the Z, Y, X? No, because see, X is greater than Y. That's why it is right child of Y. We can't move X here. So we can't do like this. Right? We can't just move X on the left side of Y. But can we do that? Can we do like this? If X becomes root here and Y becomes left child of X, yes, it can be done. See, X is greater than Y. So if X becomes root, Y can be the left child of the X because Y is less than X, right? So this is correct. And you can see it became left unbalanced, right? So we can easily apply right rotation later. So that's why the first rotation is to break this zigzag. And the next rotation is basically doing that balancing the tree, because we already saw for this structure how the single rotation makes the tree balanced. Now, if you observe carefully, shifting X to Y and making Y on the left side, it is kind of a left rotation, right? Left rotation at Y, right? Because you are basically shifting Y to the left side and making X as a root. So it is left rotation at Y to break this zigzag structure. So that's why what we do, we perform the left rotation at Y first so that it breaks that zigzag nature. And then once we do the left rotation, it becomes left situation. And in previous slide, we saw that the left situation can be solved by the right rotation at Z. Right? That's why it is a double rotation. So let's say we left rotate at Y. So what is the left rotate at Y? X becomes the new root and Y becomes the left child of X. Right? And if X has any left child, it becomes the right child of Y. We understood this in a left rotation in previous slides. And then we perform the right rotation at Z. See, left rotation we performed at Y because we wanted this structure. Right? Because we wanted move X, Y here and X here. That's why we did left rotation at Y. Now we want to do right rotation at Z because we know that this is the left situation. So it can be solved using right rotation. So if we do like this, right rotate at Z, then the tree becomes like this. So now the X acts as a Y. So this is ZYX, right? So the X becomes new root. Z becomes the right child of X. And if X has any right child, previous right child, then it becomes the left child of Z. This is what the right rotation which we understood in a previous slide. Let's understand with the example. Let's say this is our binary search tree and we are adding 40 here. If we add 40 here, then the balance of the tree at node 70 will become 2. 3 minus 1, 2, which is not allowed. So how can we find ZYX? Z is 70 here because this is the smallest unbalanced tree and that is 70 is the root of it. Z is the root of that. Y is the child of Z because it is a left child because the whole tree became unbalanced because of the left subtree of the Z. And X is basically because new node is added onto the right side of the Y. So X is the right child of Y. It can be either the new node inserted or it can be the parent of the new node inserted. So we found our 3 nodes. Now T1, T2, T3, these are the subtrees which are connected to our Z, Y, X to understand in a better way. Now, if we left rotate at 30, right, we want to break this zigzag structure. So if we left rotate at 30, what will happen? 50 will become the root here, and 30 will become the left child of 50. And if 50 had any left child, it will basically become the right child of 30. Because see, if 50 becomes root and 30 becomes the left child of 50, then this link between 50 and 40 is broken. Now where should we add 40? 40 is less than 50. That's why it will be on the left side. But 40 is greater than 30. That's why it is added as a right child of 30. Now we did the left rotation at Y or 30. Now we need to do the right rotation at Z. Right rotate at 70. So right rotate means the left child of Z becomes the new root, which is 50, and Z becomes the right child of that new root, like this. And 50 does not have any right subtree, so that's why no change there. If it had a right child, then it would have become the left child of the Z, right? So we did the right rotation on Z, and we can see now our tree became balanced. So we understood why 2 rotations is needed. First is to break the zigzag so that we can get either the left-left situation or the right-right situation. And then we know how to solve the left-left situation and right-right situation using one rotation. Now the next situation and the last situation is right-left. So we, in the previous slide, we saw left-right. Now we'll see right-left. So it is basically Z became unbalanced because of the right subtree of it, but the new node is added onto the left side of the right child of the Z. Right? That's why it is a right-left. Now right-left. So for this, we use the right-left rotation logic to solve this. So right-left rotation is used when the AVL tree is right-heavy, means Z became heavy because of the right subtree, but unbalance is caused by the left child of the right subtree. It means that we added the new node onto the left side of that right subtree, zigzag. So we saw, right, how the 3 nodes Z, Y, X can be represented in a 4 structure. So this is the structure which represents right, left. Now how can we solve it? It performs the right rotation on Y first and then left rotation at Z. We'll understand here also why 2 rotations. So these are the subtrees to better understand the tree structure after rotations. So let's say we do on a single rotation. We thought that, okay, Z is unbalanced because of the right subtree. So why can't we just do the left rotation, right? Okay, we do the left rotation. In left rotation, the right child of Z becomes the root and Z becomes the left child of that root. And if the right child of the root have any left child, then it becomes the right child of the Z. So like this. But if we see here the tree was unbalanced. And even after one rotation, the tree is still unbalanced, right? And now tree is unbalanced at node Y. It was unbalanced at Z before, 1 minus 3 minus 2. Now it is unbalanced at Y, 3 minus 1, 2, which is not allowed in a AVL tree rules. Okay. So we can't solve it using just one single rotation. So that's why we need a 2 rotations. We need to basically break this zigzag nature. So this is the zigzag nature, ZYX. Can we convert it like this, ZYX? No, because X is less than Y. So we can't just simply make it as a right child of Y. So we can't do like this. But can we do like this? Like make the y child as a make the y as a right child of the x. Make x root here. Then x is less than y. So if x becomes y root, then y can be right. So y can be easily made as a right child of x. So it will still hold the binary search tree property, and we can basically make or break the zigzag nature. So if we observe carefully, to make this x as a new root and y as a right child, we can see that it is a right rotation. The right rotation where? Right rotation at a y, right? So the first is right rotation at y to break the zigzag nature here. And then we do the left rotation at z, right? As to solve. Because see, in a previous slide we saw that we broke the zigzag nature, and but now the situation is right. So how can we solve the right situation, which we understood in the previous slides? The right situation, or when the tree is right heavy for the node Z, then we do the left rotation. So we do the left rotation as a second rotation at the node Z. That's why we need a two rotations. For example, we do the right rotation at Y to break the zigzag nature. So the tree will become like this. X became the new root, right? And Y became the right child of X, and basically the right child of X will be now left child of Y, right? Because see, if X becomes root, then T3 is greater than X, right? As we saw in the right rotation, T3 is greater than X, so it will be on the right side of X only after rotation. But T3 is less than Y, because here T3 was on the left side of Y. So it will be still on the left side of Y. So if X have any right child, it becomes the left child of the Y. So we did the right rotation at Y. So the tree became like this, and this is a right situation, which can be easily solved by left rotation at Z. So left rotate at Z, then the tree becomes like this. Left rotate at Z means the right child of this Z becomes new root, which is X, and Z becomes the left child of that new root. And now because X became the new root and Z became the left child of X, then the link between X and T2 is broken. Now T2 is greater than Z, but T2 is less than X. So T2 is less than X, so it will be on the left side of X. But T2 is greater than Z, so that's why it will be added as a right child of Z, like the left rotation logic which we understood in a previous slide. So using these two rotations, we can achieve the balanced tree for this right-left situation. Let's understand with the example. Let's say this is our binary search tree, and we are now adding 75 new node here. So the tree becomes unbalanced at node 50, 1 minus 3 minus 2. So these are the steps. Perform right rotation at Y to break the zigzag nature. What is ZYX? This is the ZYX. Z is the root of the smallest impacted subtree, which is 50. And Y is the taller child of 50, which is 80, because this is the child where the height is more. And X is basically the child of Y where the new node is inserted. It could be either new node or it could be parent of the new node. In this case, it is a parent of a new node. Now we got the ZYX. How we come to know it is a right-left rotation? First is if the balance is greater than, less than -1, it means it is right unbalanced. But the new node is added as a added to the left side of the basically added as a child of left node for the Y, then it is a right-left, right? So what we do basically, this is a T1, T2, T4 to better understand. the rotation structure. Now we do right rotation at 80 to break the zigzag structure. So 70 becomes the right rotation, means 80 becomes the right side. The left child of 80 becomes the new root, which is 70. Now 80 becomes the right child of 70. That's why this link is broken. So where the 75 will go according to the right rotation, if the left child of basically if y has any right child, then it will be on to the right side only here, right? So, but it will be as a left child of the 80, right? 80 moved here, and it will be left side of the 80 because 75 is less than 80. And 70 is less than 75, that's why 75 is on the right side of 70, right? So basically it is a right rotation logic which we understood in the previous slides, but the right rotation is at y, not on z. And now because of that, we broke the zigzag structure. Now the tree is now right. And we know that right situation can be solved using left rotation at z. So we do the left rotation at z. So which is 50. Left rotation at z means the right child of the z becomes root. And the root becomes the left child of that. Or basically the z becomes the left child of new root, which is 70 here. And if suppose the new root, which became, if it had any left child, then it becomes the right child of the z. Now there is no left child for 70, that's why there is no change. So basically this is the left rotation logic. And once we do the left rotation on 50, the tree becomes balanced like this, right? So we understood the right-left rotation logic, or basically the situation where right-left unbalance is there, then we apply the right-left rotation like this to make it balanced. So in this video, we understood what is the problem with the binary search tree, how the order of insertion and deletion makes the binary search tree unbalanced, and what is the impact of it on the performance of search, insert, or delete operation. And there are different ways to make the binary search tree balanced. There are different types of balanced trees. Then we understood the AVL tree, which is one of the type of balanced tree to make the unbalanced binary search tree to balance. Then we understood based on what balance factor AVL tree considers itself unbalanced. And then we understood the idea behind the self-balancing logic and different rotations based on that self-balancing logic. Basically, AVL tree works with 3 nodes. Why it works with 3 nodes, that we understood. And based on the structure of those 3 nodes, Z, Y, X, we have 4 type of rotations to handle those 4 type of structures, which is left rotation, right rotation, left-right rotation, and right-left rotation. And we understood the rotation logic for each case. So hope you understood the explanation and understood the AVL tree rotation concept in a detail and how it do the self-balancing to balance the binary search tree in case whenever it becomes unbalanced for any new node insertion or node deletion. And you also fully understood the core idea behind the AVL tree self-balancing logic. If you like the video, please share and subscribe. Thank you so much.